Transistors are the backbones of modern computer processors. A transistor is fundamentally just a switch that computers can toggle off and on extremely quickly. Remember that computers speak the language of binary, so when the transistor is on, it stores a 1. When it's off, it stores a 0. By toggling these transistors on and off, computers can store and process data, communicate with other computers, and do mathematical operations. One of the reasons why computers have become so much faster over the last 2 decades is because we figured out how to make transistors smaller than ever. In fact, a modern computer processor contains over 1 billion nanoscale transistors, each of which can be toggled off and on billions of times per second. But to make computers faster than ever before, and to enable new technologies like flexible electronics and wearable devices, we need to make transistors smaller than they've ever been made before. But of course, fabricating and testing new designs and new types of transistors is challenging. So instead of physically building and testing them, I use computer simulations to predict the performance of ultra-scale transistors made from 2-dimensional materials. This way, I can investigate the physics of new designs and estimate their performance limitations without ever actually having to build a single device. Then, once we know what does and doesn't work, I can share my results with experimental groups so that these findings can be implemented and tested in real devices. This saves a lot of time because we don't have to spend a lot of experimental work figuring out how to build and test new devices that might have not even been able to work from a theoretical perspective in the first place. I mostly focus on looking at how the electrostatics of transistors can be improved. In particular, I study how adding new materials into transistors and changing the geometry of transistors will affect how electric fields move around inside of them, which is a very important consideration when you're designing new transistors, and this is especially important at such small length scales. Some of the materials I've tested so far include 2-dimensional semiconductors and insulators that are made of nanocomposites. These all have an interesting material property called an anisotropic permittivity, which means that electric fields move through them differently in every direction. This has let me engineer these devices with new precision and investigate new behaviors which have never before been observed in these devices. The ultimate goal of my research is to establish design rules and guidelines and to identify new materials that could be especially useful in future transistors. So through my work, I hope to accelerate the growth in the field of nanoelectronics and to help experimentalists realize new technologies that will revolutionize what we do. Thank you.